Okay, in this video, this is 1B, and we're looking at two things: little equations, where you're solving for a variable in terms of other variables, and inequalities, where it's no longer just a single answer, but a range or a set of answers. So let's first look at little equations. Here's a couple two introductory ones. Notice in this equation we have two variables. We have an x, and then we have a y. So if we say solve for x, so to solve for anything, you get everything else to the other side. So I'm going to move the 3y over, and then we simply divide by 8, and we have this here. But notice we have a y in the answer. That's okay. And we do this because we want to isolate a variable. So then in the later, if we go ahead and figure out what y is, we can simply evaluate, plug it in for y, and then find that answer pretty simply. So we're basically isolating a variable in terms of other variables. Let's take a look here at another example. So notice here, solve for y. So how do we get y by itself? Well, the first thing we have to do is undo division of 3. So we multiply by 3. So you have the 3c over here, and the fraction's gone. That's basically called clearing fractions. And then the last thing we do is we move the y to the other side. So we subtract a. A is a variable, but it's still a number. So you treat it as like anything else, and you say, okay, how do we move addition? Well, you subtract it. So you subtract a, and you put it to the other side. So y is the same thing as 3c minus a. Okay, so that's what we're shooting for there. All right, let's take a look here at a couple other examples. Okay. Notice I throw this in here too because a equals pi times ab. Okay, so it says solve for a. So the first thing I want to do is little a over here. So I need to move both the pi and the b. So pi is a number, and b is a number. It's a variable, but it's a number. And we need to divide both of them out because they're being multiplied. So we divide both sides by pi and b, and now we have a isolated. Okay, so notice here it says isolate first and then evaluate. So now it tells us if big A is 15 and little b is 2, find a. So instead of solving back from the beginning, you just plug it into where you're at right here. 15 goes there for a, 2 in for b, and then we evaluate 15 over 2 pi as our answer. And we leave our answer like that because that's irrational. So that's the whole purpose of literal, is to isolate a variable, and then you can later simplify it and not have to go through all the algebra again. Same thing here. Now notice in this example it says solve for x, but we have two x's, but it's a common piece in both terms. So how do we take it out? We factor it out. So we take an x out of here and x out of here, and it's like reverse distribution. And then it's x times a certain quantity. So how do you get rid of this quantity? Well, you simply divide the quantity out. So divide both sides by AC. AC, in parentheses, is a number. So it's x times a number. How do you undo multiplication? You simply divide it out. Okay, so that's the value we're looking at for here. Okay, so that pretty much covers that. Now here's another example with little equations. Again, these are just showing those common algebra shortcuts or processes that you use. So here we have a fraction equal to a fraction. So if that's the case, then the numerator versus denominator on both sides have to be the same. So a good way to do this is like clearing the fractions for both sides, which is cross multiplication. So 6x and 3 go together, come over here, and then 5 times this expression go over here, and simply just distribute out, combine like terms, and solve. And notice we have x equals 5y because there are two variables in there. So cross multiplication is another great example of how to handle fractions. Okay, now we're talking about linear inequalities. Inequalities are range of answers. So I'm talking about, okay, students in the class that are older than 15. So it'd be 16, 17, 18, and so forth. So things we have to keep in mind of, if I change the statement, said, okay, students that are 15 and older. So then 15 would be included. So how do we show that mathematically? Included means solid circle or a line underneath the inequality. And not included is this over here, open circle or nor line. Okay, so this is stuff we should have seen before. So we're talking about this expression is bigger than or equal to 3. So notice when I solve it, I don't put an equal sign over here. I just put a line saying I'm comparing this expression and this expression. Okay, I'm sorry, over here I'm showing what operation I'm doing. So here, how to get rid of the 1/2? You multiply by 2. That should say 2 there. And then what do we do is now we move, because we first have to get obviously the parentheses by itself. And then you move the 2 to the other side, divide, and x is now bigger than 2. So how do we show it on a number line? Well, a number line I like to show perhaps a 0. 2 is on the positive half, it's included, so an open circle, and since x is bigger than the quantity, it's going to the right. Okay. Now over here, obviously we see a negative number, so it's basically taking the opposite. So what's the opposite of the answer that's bigger than 2? Well, if you take the opposite of x, you have to take the opposite sign. So notice we switched the signs here. So it was greater than, now less than, so x is less than -1. So anytime you have a negative multiplying or divide and you introduce it, you have to switch the signs. Okay, now these are compound linear inequalities. This is where you combine multiple things together. Okay, so let's talk about and situations. And means you satisfy both equations. So let's talk about a movie theater. Let's say you get a $4 ticket if you're, under 12 years old. And let's say you get a $4 ticket if you're a senior citizen and over 65. If you're in between 11 and 65, then it's full price and it's $8. So an and statement would be the in between. Okay, so folks that are bigger than 11 and less than 65 at the same time. So they're the in between statement, and they would satisfy this. So anytime you have an and, it's basically having like two equal signs. So notice here I put the lines in, and I'm not worried about the inequalities. What I like to do is, if I get x by itself, then I'm going to move the 7, divide by -3, and I do that. And then I go back and look at my work. It says, okay, did I multiply or divide by a negative? Well, right here I did, -3. So then I need to switch the signs. And I just had to switch them once. So it was less than, now bigger than. And if I graph it on a number line, and is always in between. So you have their two endpoints. So like the movie theater example would be 11 and 65, and it's everybody in between. So and is always in between. Now an or statement is, for instance, who has tickets that are only $4? Well, the people that are less than 11 years old, or the people that are senior citizens. So you have two different sets, but they both satisfy the answer to the question, who has discounted tickets. So in this case, it's basically you solve this set and you solve this set, but you graph them on the same number line. So notice an or example is they repel each other. So here's like less than 11 years old, and here's older than 65 senior citizens. So they don't touch, but they still are the correct solutions to the overall problem of who has discounted tickets. So again, I'm using that analogy to show why the graph looks this way. But here, obviously, in this problem, an or is always the outside of the repel. So in between is and, outside is or. So when you graph them, you want to make sure it matches your statement. Now here, notice it doesn't say and because we understood it because the statement or the expression's in between the inequalities. Okay, now in this example, we're looking at a word problem that involves inequalities. Now, let's talk about why it's an inequality. So here it says you budget $50 a month to rent movies. It costs you $36 a year and $4 per movie. Okay, and it's asking how many movies can you rent per month. So per month is pretty key. So let's first talk about why is it inequality. You have a $50 budget. So if you don't spend $50, you only spend $40, that's fine too. So it's not just what's equal to 50. Any number that produces a budget less than 50 is fine. So that's why we're looking for an expression that is less than or equal to $50. So long as you don't go over 50, you're fine. Now, why is it $3? Where does that come from? Well, here we have $36 annually. And here we're talking about how much does it cost per month. So if it's $36 annually, that comes out to $3 per month. So out of a monthly budget, it's $4 per movie plus $3 per month, which accounts for the annual cost. So that's where we're talking about units between year and month, and you have to do a unit conversion there. So here we simply solve for m, and notice as long as we have less than 11 and 3/4 movies, it's fine. Now obviously you can't rent a 3/4 of a movie. You missed the ending. That would be horrible. So you can only get 11 movies per month and still stay under $50. So obviously you're gonna have a couple of dollars left over to get some popcorn and pop for the movie, which obviously you have to have. Okay, and then the rest of, and again, this whole video you want to refer to the 1B notes on the drive, and you want to download those and go through these at the same time. And here are just 7 more examples during class. We will go through a lot of these examples, but feel free to take a look and try a couple of these out. Let's go ahead and start with this first slide and go ahead and try to hit some of these here. So it's these problems here again, but they're on the notes. And in fact, they might even be worked out for some of them.